Okay, welcome to Daily Task 7. Now in this task we are dealing with the electronic structure and electronic configuration of the elements in the periodic table, with using just a couple of the examples to help us to understand what these terms mean and how to use them if we're ever asked to. Now previously we looked at using the electrons, so the periodic table, to be able to find the number of protons, electrons and neutrons. In this case, we need to know the number of electrons to help us do this task. So what we know is the atomic number gives us the number of protons. We also know that an atom is a neutral substance, which means the number of protons equals the number of electrons. Okay, there's no overall charge on an atom. So all the elements in the periodic table as they stand are atoms. Okay, and we're going to use the fact that they are atoms to be able to find the number of electrons using the atomic number to be able to complete this task. Lithium is our first example, and lithium on the periodic table has an atomic number of 3, which means it has 3 electrons. I'm going to write them all down first, okay? Sodium is our next one on the periodic table. It has 11 as its atomic number, which means it's got 11 electrons as well as protons. Chlorine on our periodic table has an atomic number of 17, which means it has 17 electrons. And finally, aluminium has an atomic number of 13, which means it has 13 electrons. Okay, so we've used our periodic table, we've got the information that we need. In order to complete an electronic structure, and that is fill in the electron shells of an atom to show where all the electrons live, we can find them all in an atom. We need to know the rule of 8. And we cannot just put these electrons throughout these rings randomly. We can't sprinkle them like confetti throughout the rings. We have to follow the rules. Okay. The first rule is the very first shell, the innermost electron shell, can only hold 2 electrons maximum. Okay, no more than that. It can hold less, it cannot hold more. Every shell, so every subsequent shell, so every shell after the innermost one, can hold a maximum of 8 electrons. No more than that. It can hold less, but it cannot hold more than that. And each shell, starting from the middle outwards, must be completely filled following these rules before you move to the next shell. Just like in games where you have to complete each level before you move on to the next, in filling electron shells you need to complete each electron shell to its full capacity before moving to the next one. Okay, so following these rules, lithium has 3 electrons. We need to place all those 3 electrons in these shells, fulfilling these rules. So our first rule is only can have 2 electrons total in that first shell. We've got 3 to fill. We put 2 in that first shell, denoted by crosses. Okay, and then we've got 1 left to put in to a shell. We can now move to the next electron shell and put our final electron. Okay, we haven't broken any rules. 2 for the first one, and our next one can hold up to 8. It can hold less than 8, it cannot hold more. So all 3 are distributed correctly within those shells. Sodium, the next one. Okay, first shell can only hold a maximum of 2. So let's put 2 of those 11 into there. Okay, got 2 in there, we've still got another 9 to fill. Our next shell we're going to move to now, because this one is full, and we're going to put 8 electrons. I like to do them in pairs because it's much easier to keep count of what you have filled. So 8 plus the 2, we've filled 10 already. We've filled that shell, we filled the next shell, can't have any more than 8. The next one, we've got 1 more to put in, so now we can move to the outermost shell and fill that 1 electron. Okay, complete. Chlorine. I left these ones blank purposely so that we can do this. You know how to do this if you would face a blank bit of paper. So first shell, we've got 17 electrons to fill. I'm going to put 2 electrons there. We've still got 15 to fill. So let's add another shell. And we know this shell, we can add up to 8 electrons. So 2, 4, 6, 8, and it's full. We've only added 10 already, all those together. 2 plus that 8, we need to add another 7. So we're going to have to add another shell. So we've added 10 already, 2 to fill the first one, 8 to fill the second one. That gives us 10 in total. We're left with 7. 2, 4, 6, 7. And they're all distributed following these rules, all 17. Aluminium, we have 13 electrons to fill this time. The first shell can only hold 2. We need to move to the next shell. This shell can hold a maximum of 8. 2, 4, 6, 8. That 8 plus the inner 2 equals 10. We've got 13 to fill all together. So we'll have to add another shell. 1, 2, 3. 13 electrons filled in those shells following those rules. Good. Okay. You can try this for different elements. Have a go, have a practice. Okay, or recreate these to practice as well without looking at your notes. Okay, so these are the electronic structures. So electronic. And to help me remember and help you remember the difference between electronic structure, and then we're changing it to electronic configuration. Electron configuration. Structure, if you think of a building is a structure, and a structure shows you what something looks like if you could see how it was built. Okay, in this case, our structure of the shells is this diagram, okay, of what it would look like if you could see those electron shells. The electron configuration is how each of those electrons is configured per shell. And it's quite straightforward. You just start at the middle innermost shell and write down the number of electrons that are in it. In this case, there are 2. Then we move to our next shell, put a little dot to denote the fact that we are moving to the next shell, and we write down the number of electrons that are in that next shell. In this case, for lithium, there is 1. Okay? For sodium, okay, you can imagine you're a little person in here and you're walking through the shells and counting the electrons as you go. So the first shell you hit has 2 electrons. Put a little dot to denote the fact that you're crossing that line to the next electron, the electron shell. The next electron shell has 8 in it, so we write down 8. Little dot to show we're crossing over that into the next shell. The next shell holds just 1 electron. Okay, let's try for chlorine. Imagine you're standing in the middle and you're going to walk through the shells one at a time. The first shell you see has 2 electrons. Put a little dot to show that you've crossed over into the next shell. That next shell has 8 electrons. Again, a little dot to show you've moved again to the next shell again. And this outer shell here has 7 electrons. No more shells, you stop your writing there. Aluminium. The first shell has 2 electrons. Put a little dot to say you move into the next shell. 2, 4, 6, 8 electrons. And the outermost shell has 1, 2, 3 electrons. So these are your structures, what they look like in a diagram, and your configuration, how those numbers are used to represent the number of electrons in each shell. Okay, you can do that for any diagrams that you choose. We fill in the electrons in the shells. Right, now, something that we can use this information for is to find any trends in the periodic table. Now let's look at lithium to start with. We can use our electronic structure and configuration to help us to decide on the trends that we can see. Now, lithium is in group 1. This is group 1, 2, 3, 4, 5, 6, 7, and 8, or 0. Okay. Lithium is in group 1. Lithium also happens to have one outer shell electron. Number 1 at the end there. Okay. It has one outer shell electron, which means it is put into group 1. Okay, let's have a look at sodium. Sodium, if that rule is true, sodium has one outer shell electron. It should be in group 1. And there it is in group 1. Okay, let's have a look here. Chlorine has 7 in its outer shell, 7 electrons in its outermost shell. Okay, it is in group 7. And aluminium has 1, 2, 3 electrons in its outermost shell, which means it should be in group 3. Was aluminium? Yes, it's in group 3. So the number of valence or outer shell electrons is the same number as the group that the element is in. It's in that group because of the number of electrons that it has in its outer shell. But what about how high or low it is? What about what period it's in? So the periods go across this way. How does that relate? Well, let's have a look. Lithium has 1, 2 electron shells that are occupied by electrons. 1, 2. There's 2 numbers there, which means there's 2 shells occupied by electrons. Lithium is in period 2. It's in period 2 because it has 2 shells that are occupied by electrons. 2 electron shells with electrons. Let's see if that rule works here. Sodium, 3 sets of numbers, 1, 2, 3 sets of shells that have electrons in them. So 3 occupied electron shells. If that rule is correct, it should be in period 3. Let's have a look. Sodium, it is indeed in period 3. Okay, 1, 2, 3. Chlorine, again, has 3 sets of numbers, which means it's got 3 occupied electron shells. 1, 2, 3 should be in period 3. That's period 1, period 2, period 3. There's chlorine, period 3. And finally, aluminium, again, has 3 sets of numbers. 1, 2, 3. 1, 2, 3 shells, what that means. So again, it should be in period 3. And there we go, 1, 2, 3. There's aluminium. Every position in this periodic table is dictated by the number of valence electrons and the number of electron shells occupied by electrons. So oxygen, if you drew that out, the electronic structure of oxygen, to check you've done it correctly, being in period 2, there should be 2 electron shells that have electrons in them, and the outermost number of electrons should be 6 because it's in group 6. If you did carbon, again, it's in period 2, which means you should have 2 electron shells that have electrons in them. They don't have to be full, they just have to have electron shells in them. Okay, electrons in them, sorry. And it's in group 4, which means the number of electrons on the outside, the very outermost electron shell, the valence shell, should have 4 electrons in it. That's the same rule across the periodic table. Okay, have a go. Well done.